Welcome to Lesson 5.2, Extrema on an Interval. The standard for this lesson is functions-1.c.1. If a function f is continuous over the open interval ab, then the extreme value theorem guarantees that f has at least one minimum value and at least one maximum value on that open interval ab. In this lesson, we will use derivatives to find local or relative and global or absolute extrema. We will use both open interval and closed interval methods for finding extrema, i.e. the candidate's test. Finally, we will use and apply the extreme value theorem on intervals. The instructional objective for this lesson is that students will be able to apply the extreme value theorem in order to justify conclusions about functions. Our inquiry question is, how can we use existence theorems to draw conclusions about a function's behavior on an interval without precisely locating that behavior? Finally, this lesson focuses on topic 5.2 of the 2019 course and exam description of the AP Calculus AB curriculum. Extreme value theorem, global versus local extrema, and critical points. The maximum and minimum values, max and min, of a function are called the extreme values or extrema, singular extremum, of a function. The process used for finding them is referred to as optimization, and there will be times when we want to find the max and min for x on the entire domain, and at other times on a particular interval. In this lesson, we will learn how to use calculus to find extrema rather than a calculator. Let's define absolute and global extrema. An absolute or global maximum is the highest possible y value on a function for a given interval. How can we say that mathematically? Well, remember that y is equal to f of x. So we're going to consider a particular x value, call it c, and we can make the following statement. If f is a function on an interval I, then y equals f of c is the absolute or global maximum on I if and only if f of c is greater than or equal to f of x for all values of x in the interval I. Likewise, an absolute or global minimum on I occurs if and only if f of c is less than or equal to f of x for all x values on the interval I. In example 1, we're told the graph y equals h of x is shown below. Determine the extrema of h of x on the closed interval a less than or equal to x less than or equal to f. Well, let's look for both absolute and relative extrema. So on this interval from a to f, it seems like the highest possible value, our absolute maximum, might occur at x equals e. And so we'll just see if we can show that graphically. So there we have f of e. And it seems like maybe the lowest value, our absolute minimum, would occur maybe at point D. Now, this is important. This was a closed interval. That means that the endpoints were included. So when I'm looking for these absolute max and mins, I'm comparing the endpoints. The endpoints are in the game. Now, had this been an open interval, I would not consider the endpoints. And in fact, for relative min and max, we don't consider the endpoints, but we always check the endpoints if it's going to be an absolute. So let's just make a quick note. F of e is going to be a relative max, and that's going to be at x equals e, and f of d is a relative min, again at x equals d. Alright, well, what about relative maxima and minima? So if we were to constrain our interval to maybe AD, we would have a relative maxima located at f of c. So that would be a relative max. And also this cusp would be a relative minimum on that same interval. That's going to be f of b. And we can say that's a relative min. So based on example 1, here's another way that we can think about relative and absolute extrema. Relative or local extrema are just points on the graph of a function where the function changes from increasing to decreasing and vice versa. Now the absolute or global extrema, those are the highest and lowest points on the graph of a function or on a specified domain of a function. To go about finding relative or local extrema, all we have to do is be able to identify an interval on which there is a particular x value, call it c, where f of c would be the relative maximum or relative minimum. Point where, in the case of being a relative maximum, the graph changes from increasing to decreasing, and in the case of a relative minimum, changes from decreasing to increasing. So, in more mathematical language, we say, if there is an open interval containing c on which f of c is a maximum, then f of c is called a relative maximum of f. If there's an open interval containing c on which f of c is a minimum, then f of c is called a relative minimum of f. So here are a few things for us to keep in mind. When we say an open interval containing c, we mean that we can find some interval AB, not including the endpoints, such that A is less than C is less than B. So that is, C will be contained somewhere inside the interval and will not be either of the endpoints. A relative extrema is slightly different than an absolute extrema. All that's necessary for a point to be a relative max or min is for that point to be a maximum or minimum in some interval of x's around x equals c. There can be smaller or larger values of the function at some other location, but relative to x equals c, f of c is smaller or larger than all the other function values in the neighborhood of c. In example 2, we're told to consider the graph of y equals g of x, shown at right. Part A, state the relative extrema of g of x. So for relative extrema, we can consider some bounded interval on the function. So for instance, we would have a relative maximum located at 2, 2. So we could say relative max is 2 at x equals 2. And we would have a relative minimum located at 4, 0. So we could say relative min is 0 at x equals 4. In part B, considering the domain for g, what are the absolute extrema of the function? Well, this is going to be a quartic function, and so you can see that the end behavior is that the function tends to positive infinity as x goes to infinity, and positive infinity as x goes to negative infinity. And so when it comes to absolute extrema, we can say first of all that the absolute max does not exist, and the reason is because g of x is unbounded above. Now what about absolute min? So our absolute min is actually going to be this point here, -3, -8. So we can say the absolute min is -8, and that's going to be at x equals -3. In example number 3, we'll consider the graph of y equals f of x. On the bounded interval 0 less than or equal to x less than or equal to 12, shown below, find the relative extrema of f of x. Alright, so we have a relative max. Let's see, that's going to be located right about here. And this looks to be approximately 7, 7. So we can say the relative max is 7 at x equals 7. Now we have a relative min located at about the point 2, negative 2. So we can say the relative min is negative 2 at x equals 2. And we have another relative min here, and this seems to be approximately 10, 2. And so we can say relative min is 2 at x equals 10. In part B it says, considering the domain for f, what are the absolute extrema of the function? Alright, well let's start with absolute max. So remember that on a closed interval, you always want to check the endpoints when you're looking for absolute extrema. And so going across, we can see that we have a y value of 1 located at x equals 0. And so 1 is definitely not going to be our maximum for this function. Now the lowest possible point on this function, as described, seems to be negative 2. And so I think that'll be our absolute minimum. And then we have y equals 7 located at x equals 7. And you'll notice that that point is higher than our second endpoint, which is only located at y equals 6. So the highest total point on this closed interval is going to be y equals 7. So we can say the absolute max is 7 at x equals 7. And we can also say that our absolute min is negative 2 at x equals 2. But don't forget, for absolute extrema, you have to check the endpoints. And if one of the endpoints is more extreme than any other point on the open interval, then that's going to be your absolute extrema.
So what conditions would be necessary in order to have both an absolute maximum and an absolute minimum? That's where the extreme value theorem comes in. If f is continuous on a closed interval AB, then f has both a maximum value and a minimum value on the closed interval AB. Extreme values can occur at interior points or also at endpoints of an interval. A function may have both maximum and minimum values over an interval, either a maximum or a minimum, or no extrema on an interval at all. We'll look at some examples below. Also note that when the hypothesis or if statement is not met, either continuity or the closed interval, there is no guarantee of the conclusion or then statement. However, a maximum, minimum, or both may still exist. There's just no way to guarantee this. We'll see examples of this behavior as well.
In example 4, we're told for each graph below, explicitly state where the hypothesis of the extreme value theorem fails on the closed interval from 0 to 3. Then determine if the function has an extrema on the interval. So in part A, we have this piecewise linear function on the closed interval from 0 to 3, and we can see that we have a jump discontinuity located at x equals 1. So that's what we're going to say. So let's say EVT fails at x equals 1 because f is not continuous on closed interval 0, 3. Alright, now let's see about extreme values. We have a maximum value located at x equals 1 and a minimum value located at x equals 0. So let's say the absolute min is 1/2 at x equals 0, and the absolute max is 4 at x equals 1. So in this case, one of our absolute extrema was an endpoint. And so that's the reason why, since those endpoints are included on the closed interval, we have to check them when we're looking for absolute extrema. In part B, we have another piecewise defined function over the closed interval from 0 to 3. We can see we have another jump discontinuity located at approximately x equals 1.5. So let's say that EVT fails at x equals 1.5 because f is not continuous on the closed interval from 0 to 3. Now, what about absolute extrema? Well, the lowest possible point doesn't exist because it's a hole in our graph. So, you have an absolute maximum, however, located at x equals 0. So let's say that our absolute max is 4.5 at x equals 0. And we can say that our absolute min is 1, located at 1.5. The problem is that point does not exist. Alright, in part C we have a function on the closed interval from 0 to 3, and we can see that we have a vertical asymptote located at x equals 3. We have a hole located at x equals 0. And our function is approaching negative infinity as x approaches 3. So let's see, what can we say here? The extreme value theorem does not apply because f is not continuous on the closed interval 0, 3. A couple of things here. Okay, so AP test etiquette. I just called this function f, but it was not explicitly labeled f. That's okay. I'm going to come up here and say y equals f of x. And now it's all good. The AP reader will know exactly what I'm talking about when I say f. Otherwise, it's ambiguous and they won't give me that. And then there's this matter of having no extrema. And this is really kind of a direct result of this lack of continuity. The highest possible point on this graph would be 0, I guess that's maybe 4 1/4. The problem is that's a hole. That point does not exist in the graph. So the absolute maximum does not exist. Well, what about absolute minimum? Well, the function is unbounded as x approaches 3. And so it goes to negative infinity. Again, there's no minimum value. Now let's go back and talk a minute about this function not being continuous. Yes, we do have a hole located at what should be the end point. But that's not the only discontinuity. The fact that my graph approaches x equals 3 asymptotically means that there's always some gap between the function and what should be the endpoint 3. So speaking of labeling your function to match your description, let's go back and fix part A and B. So what we'll do is we'll just write y equals f of x and y equals f of x. Because the AP reader will say, we don't know what f is. F wasn't defined in the problem. But if you label it f, then that's consistent. So in part D, we'll start off with y equals f of x. And here again, we can see that we have a function that is not continuous on the closed interval because the endpoints are holes. So this would actually be a function on the open interval from 0 to 3 with the endpoints not included. So let's say the extreme value theorem fails since f is not continuous on the closed interval 0, 3 at x equals 0 and x equals 3. Now, on the interval, we do have an absolute minimum located at x equals 2, and we have an absolute maximum of 4 located at x equals 1. So let's go ahead and record that. Absolute max of 4, x equals 1. Absolute min of negative 0.75 at x equals 2. So the extreme value theorem gives us the knowledge of when extrema occur, but how will we find them algebraically when given only an equation without the benefit of a graph? So the next question should be, how can we identify all the values of x where extreme values occur? So let's take a look at that in the next example. In example 5, we're told for each function shown below, justify or explain why the extreme value theorem can be applied or why it does not apply on the given interval. So in example 5a, we have f of x equals 2x minus 3 over x minus 2, a rational function, and this is on the closed interval from negative 4 to 4. So since this is a rational function, one of the things that we want to do is to determine whether there are any vertical asymptotes or holes. So we look at the domain of this function. If you set the denominator equal to 0 and solve for x, we see that x equals 2. And that doesn't cancel with the numerator, so that'll be a vertical asymptote. Here's what we're going to write. The extreme value theorem does not apply for f of x on the closed interval from negative 4 to 4 because f is not continuous at x equals 2, which is contained on the interval. In 5b, they tell us that g of x is equal to e to the x minus 2 quantity plus 1 on the closed interval from negative 5 to 5. Well, okay, e to the x is a continuous function on all real numbers. E to the x minus 2 is nothing more than e to the x divided by e squared, and then plus 1 just shifts it up 1. So that's just a vertical transformation. So this function is going to be everywhere continuous. It's definitely continuous on our closed interval. So let's write this. G of x is continuous for all reals. So the extreme value theorem applies for g of x on closed interval negative 5 to 5. Let's look at example 5c. Here we have h of x equals x times the square root of x plus 2 on the closed interval from negative 6 to 6. H of x is a composite function. It's the product of x and the square root of x plus 2. Well, x can be everywhere continuous, so that's not a problem. But the square root of x plus 2, remember that the radicand, the expression that is under the radical, has to be non-negative. And so what that means for us is that x plus 2 has to be greater than or equal to 0, which implies that x has to be greater than or equal to negative 2. And the problem is that we have values that are less than negative 2 that are on our closed interval. So here's what we're going to say. Since h of x is continuous only for values x greater than or equal to negative 2, the extreme value theorem does not apply for h of x on the closed interval from negative 6 to 6.
A critical number or critical value of a function f is an x value, x equals c, in the domain of f such that either f prime of c is equal to 0, the slope of the tangent line is horizontal, or f prime of c does not exist or is undefined. In other words,
the slope of the tangent line is vertical. If x equals c is a critical value, then c f of c is called a critical point. So a couple of theorems based on this. Relative or local extrema can occur only at a critical value on an open interval. Absolute or global extrema must occur at a critical number or at an endpoint of an interval. Now, topic 5.5 from the AP Calculus course and exam description is using the candidates test to determine absolute or global extrema. So this is an analytic method that we can use to test all of the possible candidates for absolute extrema. And so let's think about what the candidates are. Well, we've already said if it's a closed interval, the endpoints are candidates for being absolute extrema. But what else? What are the values on the inside? Well, remember, going way back to the beginning, these are values where we have turning points in our function. And that happens where we go from increasing to decreasing or from decreasing to increasing. And what all these points have in common is that the slope of the tangent line there is equal to 0. It's a horizontal line. So for us, that means that we just need to take the derivative of the function and set it equal to 0. And then we take all of the x values that correspond to roots of the derivative. Those are called critical values. We're going to list those along with the endpoints, and that gives us all of our candidates. And so then we can check and see what the corresponding y values are, and from a t-table, make a decision about the absolute minimum, absolute maximum. So let's do this. Step 1. Let's take the derivative of our polynomial function. Now, this is a polynomial, so it is everywhere continuous, and therefore continuous on our closed interval, -1 to 2. F prime of x is going to be 24x squared minus 6x minus 9. Now, we can factor 3 out, and that's going to leave us with 8x squared minus 2x minus 3. And setting this equal to 0, we can divide the 3 out, and we have 8x squared minus 2x minus 3 equals 0. This is a calculator problem, so you could find these roots on your calculator, or you could factor it using the AC method. If you factor it by hand, we end up with 4x minus 3 times 2x plus 1 equals 0. And then solving for x, we get x equals 3/4, or x equals -1/2. And so then here we have the candidates test. So we'll have x values of -1 and -1/2 and 3/4 and 2. So the two endpoints and the two values where the slope is equal to 0. And we'll find our corresponding f of x values. And we'll just go ahead and write those as decimals. And we can plug these into our calculator and find the corresponding f of x. So if we plug in -1 for x, and we compute 8 times -1 cubed minus 3 times -1 squared minus 9 times -1 plus 2, we get 0. And if we plug in 2, we get 36. Plugging in -1/2 gives us 4.75, and plugging in 3/4, we get -3.063. So here we can see that our absolute min will be -3.063 63 reported to 3 decimal places, and our absolute max is going to be 36. In part B, we have g of x equals x minus 2 sine x on the closed interval 0 to 2 pi. So we'll begin by taking the derivative of g of x. And so we have g prime of x is equal to the derivative of x is 1 minus the coefficient is 2, derivative of sine is cosine, so 1 minus 2 cosine x. So then we'll set this equal to 0, and this gives us cosine x equals 1/2. Now from the unit circle, we know that from 0 to 2 pi, so that's the full unit circle, x equals pi over 3 when cosine is 1/2, and x is also 5 pi over 3 when cosine is equal to 1/2. So now we'll do our candidates test. So we've got our first endpoint, 0, and if we plug 0 into the original function, g of x, we get sine 0 is 0 times 2 is 0, x is 0, 0 minus 0 is 0. Now at pi over 3, we'll just put this function into our calculator and substitute pi over 3 into it. We get negative 0.685 to 3 decimal places. Then we'll do 5 pi over 3, and that's going to give us 6.968. And then finally our last endpoint, 2 pi, and at this point we get 6.283 from our original function. And so we can conclude that our global minimum is going to be negative 0.685, that's the lowest value, and our maximum is 6.968. So just barely beating out this. In part C, we have h of x equals sine squared x minus cosine x on the closed interval from 0 to 3 pi over 2. Start by finding the derivative of h of x. So we have h prime x is equal to, now notice here we have sine raised to a power. We're going to use the chain rule, and so we begin with the derivative of the exponent. So power rule is 2 times the inside function, which is sine x, to the first power. So power times base down 1. But now, via the chain rule, I have to multiply by the derivative of the inside function. And the derivative of sine x is cosine x. And that's going to be minus the derivative of cosine of x. But the derivative of cosine of x is negative sine of x. And so that'll become positive minus a negative sine x gives us plus sine x. And this will be equal to 0. So let's solve this. So if we factor out a sine x, that's going to leave us with 2 cosine x plus 1 in parentheses equals 0. And we have sine x equals 0, or cosine x equals negative 1/2. Okay, so this is going to happen when x equals 0, pi, and then for cosine at 2 pi over 3 and 4 pi over 3. And remember, we're on the unit circle, but we're only going around to 3 pi over 2, or 270 degrees. So let's do our candidates test. And our first endpoint is 0, and this also corresponds to one of our roots of the derivative. So we've got that one when we got the endpoint. And then our next larger value will be 2 pi over 3, and then pi, and then 4 pi over 3, and then finally our last endpoint, 3 pi over 2. And so what I would do is I would put this function into my graphing calculator as y1, and just substitute these values one after another and see what I get. So 0 goes into this original function, and we get back out -1. 2 pi over 3 gives us 1.25. Pi is 1. 4 pi over 3 is 1.25. And 3 pi over 2 is 1. So our minimum value is -1. And our maximum value is 1.25. In part D, we have another composite function. F of x equals the natural log of x squared minus 9 on the closed interval from -2 to 5. Now, for the natural log, remember that the natural log, it has a domain which is all positive real numbers. And so that means that x squared minus 9 has to be greater than 0, strictly greater than 0. And so let's do that. Let's start with x squared minus 9 greater than 0. And so if we factor the left side, we get x minus 3 times x plus 3 greater than 0. And this gives us our x-intercepts, factoring as a difference of squares. And so let's just take a minute and think about this x squared minus 9. Now, you can certainly do this on a calculator, but I think quadratics are pretty familiar functions for us. So here is a real quick representation of what's going on. So I have a point at -3 and a point at +3. This graph opens up because the lead coefficient is positive. So I'm not even going to worry about, graphing this exactly. I'm just wanting to sketch this. And so what I can see is, since it's an upward facing parabola and it has x-intercepts at -3 to +3, for this inequality, that means that when is x squared minus 9 less than or equal to 0? So it's greater than 0, this part up here, but it's less than or equal to 0 down here. So we can say x squared minus 9 is less than or equal to 0 on -3 is less than or equal to x is less than or equal to +3. So here's what we're going to say. F of x is not continuous on -2, 5, since the domain of f of x is undefined from -3 less than or equal to x less than or equal to 3. So the extreme value theorem does not apply. In E, we have another composite function, so chain rule again. H of x is the cube root of x minus 2 quantity squared, and that's going to be on the interval from 1 to 10. So let's take the derivative. We can rewrite this as x minus 2 to the 2/3 power. And I like to do that with problems that have radicals because it lets me use the power rule. So h prime of x is going to be now 2/3 times x minus 2 to the, and now I have to think about this. It's power times base down 1. So 2/3 minus 1 is the same as 2/3 minus 3/3, and this gives me -1/3 as my exponent. So that means that this is going to be 2/3 x minus 2 to the 1/3 power, or I could rewrite it now as a radical again. Cube root of x minus 2. So that's 2/3 times the cube root of x minus 2. And of course, we're going to set this equal to 0 so that we can solve. Now, this is a rational function, so we need to check and see when is the denominator equal to 0. So the denominator is going to be equal to 0 anytime the cube root of x minus 2 is equal to 0. And that's going to happen when x is equal to 2. Now I don't have to worry about setting the radicand greater than or equal to 0 because you can take the cube root of a negative number. So negative numbers are not going to be a problem. It's just that 0. So here's what we can say. We can say h prime of x is not equal to 0. So there's no value of x that will make it equal to 0. And furthermore, h prime of x does not exist when x equals 2. Alright, so how do I know that it's never equal to 0? Well, you could graph it on your calculator, but I can multiply through an equation by anything so long as it's not equal to 0. If we eliminate 2 from the domain, the denominator will never be 0. And if we multiply through the equation by the 3 times the cube root of x minus 2, we end up with 0. It 0 times this expression, and it goes away. So that's one way of showing that this can never be equal to 0. There's no value of x that would cause this to be equal to 0. So we've got critical points, though. And so what are they? Well, the endpoints, 1 and 10. And also where the function is undefined at x equals 2. So we have 3 values we're going to check for our candidates test. So our first endpoint is 1, substituting 1 back into h of x. h of 1 is 1. h of 2 is 0. h of 10 is 4. So our minimum value is 0. Our maximum value is 4. And so that's going to be it for lesson 5.2, but we've still got more to come in this unit. We're going to be doing, I think, some curve sketching next, so we'll see you in lesson 5.3.